Part 4, the inverse of a function. Okay, the inverse of a relation is found by interchanging the x and y coordinates of the points and or equation. The resulting graph represents a reflection over the line y equals x. Therefore, any point on the line y equals x has to be an invariant point, right? That's the new mirror. Okay, the mapping rule is xy maps to yx. Okay, if the x and y coordinates are just switched, that would mean all the x attributes of the original function are y attributes on the inverse function. Similarly, all y attributes on the original would be x attributes on the inverse. So what does that mean? Okay, it means that the x-intercepts on the original are now y-intercepts on the inverse. It means that y-intercepts on the original are now x-intercepts on the inverse. The domain of the original is now the range of the inverse, and the range of the original is now the domain of the inverse. These will all be demonstrated in the examples. Now, there's several ways to express an inverse function or an inverse relation. Okay, the first one is just x equals f of y. Okay, or we could go y equals f negative 1 of x. Okay, so that works. Okay, so there's just different ways of saying an inverse relation. Okay, the inverse of a function may or may not be a function. Okay, recall that to be a function there can only be one y for every x. This means the graph has to pass the vertical line test. Wow, this was way back in grade 10. If you draw a vertical line anywhere on the graph and it intersects two or more points, then the graph is not a function, it's called a relation. So let's just do a quick couple sketches here. So this guy here, okay, so just the basic parabola, okay, right in blue now, okay, you can draw a vertical line anywhere on this and it would only hit one point. Okay, so that graph is a function. Now, if you have something like this, here I'll draw different colors just make it easier. Okay, if you have a graph that looks like this, okay, here we'll draw an orange now. So look, if you draw the vertical line, oh, it touches 2 points. So this one was a function. This one is not a function. So it's still called a relation, but it's just not a function. Okay, fair enough. Okay, so example 1. Consider the graph of the relation shown. Now, is that a function? Sure it is. Now you can draw a vertical line anywhere, okay, and it doesn't touch more than 1 point, so that is a function. Okay, great. Easy enough. Now, sketch the inverse of this relation. Okay, so I'm going to go back to my blue pen because it shows up fairly nice. Remember, all an inverse is, it's a reflection over the line y equals x, and I'll show you that here in a minute. But what we do is we take each individual point and we switch the x and y coordinates. So if we have a look at this guy, that point right on the end, that is 1, 2, 3, 4, 5, 6, 7. So negative 7, 1, 2, 3, 4, 5. So that's negative 7, positive 5. So to take the inverse, we just switch the x and y coordinates. So it's going to be 5, negative 7. So look at where that goes. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. So 5, negative 7 goes right here. Awesome. So this one, okay, so that is, let's see, 1, 2, 3, 4, 5. Okay, so negative 5 and positive 7. So negative 5, positive 7. So that goes to 7, negative 5. So 7, negative 5 is there. Okay, awesome. All right, the next corner is that one. So that is the point 0, 7. Hey, look, that's an y-intercept here. So over here, it's going to be an x-intercept. So that is, okay, so 0, 7. So now it goes to 7, 0. So that's right there. 7, 0. See what I mean? The y-intercept becomes an x-intercept. Okay, great. Okay, so this next corner is right there. So that is the point 1, 2, 3, 4. 1, 2, so that's the point 4, 4. Okay, well, oh boy, if the point 4, 4 switches x and y coordinates, well, it's still 4, 4. Okay, so that point's going to illustrate the invariant point. Okay, that one doesn't move. Okay, so this guy is at 6, 4, so now he goes to 4, 6. Okay, and then this last point is at 8, 0. So we just switch him, so now he's at 0, 8. So that goes right to there. Okay, and now we just connect the dots. So here, here, there, there, and there. Okay, now I'm going to draw another line here. So remember we said that this was the reflection in the line y equals x. So this is the line y equals x. And you can kind of see that those are reflections. It's really kind of neat, kind of looks like a spidery sort of thing, but it's very different. Okay, now, okay, so that was the sketch part. Now B says state the domain and range of the relation and its inverse. Okay, so the original, okay, and then the image. Okay, so the original, he went from -7 all the way up to +8. So negative, okay. So the domain is -7 up to +8. Okay, the range, on the other hand, the range went from 0 up to 7. So 0 up to 7. Now the image, on the other hand, so that's this blue line graph. So he goes from -7 all the way up to +8. Ooh, pardon me. That's a range. Okay. Okay. So the blue graph. Okay. So let's start with the domain. So the domain starts at 0 and goes up to 7. So 0, domain, 0, and up to 7. Okay, and then the range for this one, that went from -7 all the way to 8. So -7. Now, if you remember what I said, all the x and y attributes just change. Check this out. The domain of the original is now the range of the image. The range of the original, 0 to 7, is now the domain of the image. Right? If you just switch the x's and y's, then those now become ranges, become domains, domains become ranges, and there you have it. Okay, and you can look on the graph if you want, but you don't always have to graph these to be able to get the answers. So C, determine whether the relation and its inverse are functions. Okay, so the original, we already said that was a function because we did the vertical line test on it and it passed. There was never touched any more than 1 point. Now, the inverse though. Okay, and let's see. We can find, oh, look at green. We can use that. Okay, if you look at the inverse, if you look right here, I know it's kind of hard to see, but if you draw a vertical line there, it touches a couple of points. So the inverse is not a function. Okay? Because it does not pass the vertical line test. Okay? Now, state the coordinates of any invariant points. Wow, I kind of messed that up, but we talked about it earlier. It was the point that was right here. That was the point 4, 4. Okay? And that's actually on that dotted x equal y line that's on the mirror. Okay? All right. So just like we have to check if a graph represents a function by a vertical line test, we can do something similar to test if the inverse is a function. If we draw the inverse function, we can always do the vertical line test on that. Okay? That's an effective way of doing it, but you have to draw the inverse. Okay, like we did in the example here. We drew the inverse, we found out it didn't pass the vertical line test, so it's not a function. However, another way, because the function's inverse are always reflections over the line y equals x, another way to check if the inverse is a function is to perform a horizontal line test on the original function. If the graph touches two or more points on a horizontal line drawn anywhere through the graph, then the inverse will not be a function. So tell you what, guys, I'm going to scroll up here and I'm going to erase all this stuff. And it's recording, so you can always rewind and get it back if you want. But I just want to illustrate what that means. Okay, so look, the vertical line test, okay, it doesn't touch any more, just one point, so the original is a function. But if I want to know if the inverse will be a function without actually drawing it, all I have to do is do the horizontal line test here. Okay, the horizontal line test fails right here because it touches all those points. Okay, so this guy failed the horizontal line test. So even though the original is a function, the inverse will not be because it failed that horizontal line test. Cool, it's a nice way of doing it without actually having to draw it. Okay, so now, if the inverse is not a function, we can make it one by restricting the domain of the original function. Okay, that sounds a little weird, but it's not so bad. Okay, so let's have a look at this example. And you know what? I'll change back to blue because I think it shows up best. Okay, so consider the function y equals x squared minus 2. Okay, so I want you to sketch the function. So x squared minus 2, that is just a parabola. It goes through minus 2. Remember, there's that pattern we talked about. Over 1, up the odds. So over 1, up 1. Over 1, up 3. 1, 2, 3. 2, 3. Okay, and then over 1, up 5. 1, 2, 3, 4, 5. For 1, 2, 3, 4, 5. So that is a pretty accurate sketch of this graph. Okay, now, so we sketched the function. Is the inverse of f of x a function? Okay, we could draw it. We could draw the inverse if I really wanted, but that's the whole point of showing you that shortcut. Okay, so look, if we draw a horizontal line touches more than one point. So is the inverse a function? No. Okay, the original failed the horizontal line test. That means the inverse will not be a function. And that does make sense, because if we were, here I'm going to erase that line, so no. Okay, because if we were to draw the inverse, it would look kind of like this. Oh, look, then it fails the vertical line test. Okay, so either way you do it, it's not a function. Just doing it the first way, you just don't have to draw it. Okay, awesome. So then it says, what is the x-intercept of the inverse? Well, the x-intercept of the inverse, remember, that's a y-intercept on the original. Okay, well, the y-intercept on the original is negative 2. So negative 2, 0. So the x-intercept, oops, I did that wrong. Got ahead of myself. So the y-intercept on the original is 0, negative 2. Okay, so that's going to be, that's on the original. So on the inverse, so that's going to be the x-intercept on the inverse. And we just switch the x and the y, so it's going to be negative 2, 0. Okay, so negative 2, 0, so 1, 2. So that's going to be right there. Okay, now graph the inverse on the same set of so on the same graph. Okay, so remember the pattern. We talked a little bit about this earlier. The pattern for these, it's still, instead of 1 over 1 up or 1 over up the odds, this is going to be 1 up over the odds. It's just the XY pattern changes. So up and down 1, So there and there. Okay, up another one over 3. Up another one over 5. So 1, 2, 3, 4, 5. Okay, 2, 3, and 5. Okay, so that's, again, a pretty accurate graph of the inverse. Okay, it looks like that. Great. Okay, now, that clearly isn't a function, right? It totally isn't. Okay, so describe how the domain of f of x could be restricted so that the inverse of f of x is a function. So how we do this, everyone, and this is tricky, so you have to wrap your head around it. Okay, I'm going to hit undo so we can get rid of that graph for just a second. The idea is, if we restrict the domain, we get rid of part of it. So, and what we want to get rid of is 1/2 of the graph. So we get rid of either one side or the other. Okay, so tell you what, if I say that x is bigger than or equal, so make the domain, so x is bigger than or equal to 0. Look what this becomes. This graph becomes this. Okay, so only the x is bigger than 0 parts are allowed. Okay, now look, if I restrict the domain like that, does it pass the horizontal line test? Well, sure it does, because there's nothing over on this other side anymore, because I restricted the domain. Okay, I just made it so that the negative x values aren't allowed. Okay, so that when I take the inverse of it now, okay, when I take the inverse of it now, it looks like this, and hey, that's now a function. Okay, so I could restrict the domain like that, so x is bigger than or equal to 0. Now, there's the other answer too, because I could have restricted it the other way. Right? I could have just said, okay, we're going to have the negative x value. So we could say that x is less than or equal to 0. Okay, when I do the inverse of that one, okay, that side, it just looks like this now, which is still a function. Okay, so the idea is you restrict the domain right down the axis of symmetry. Okay, and you make it either bigger or smaller than that, so that restricts the domain of the original, so that when you take the inverse of it, the inverse will still be a function. Wow, it's kind of heady, but that's okay. So, tell you what, it's kind of a small part, so don't lose sleep over it. But that's the idea. You restrict the domain, so just right down the axis of symmetry. Okay, so last one. Okay, sample 3. Okay, algebraically determine the equation of the inverse for each function. Okay, verify graphically that the relations are inverses of each other. So, the idea here is we take these two things and we switch the x and y coordinates and then resolve for y. So we say x equals 3y plus 6. Okay, then we solve for y again. So we go minus 6, minus 6. So x minus 6 equals 3y. Divide by 3, divide by 3. So we divide each term by 3, right? So that makes y equals, so 1/3 x minus 2. Okay, and when we graph this on our graphing calculators, it's quite obvious or quite easy to see that those are reflections. Now, I'll show you that here in just a minute because I cheated a little bit, but that's okay. We'll get there in a second. All right, so then the next one, we switch the x and y again. So x equals y squared minus 4. Okay, plus 4, plus 4. So x plus 4 equals y squared. So then we square root. Now remember, when you square root, you're supposed to have a plus minus. So y equals plus or minus x plus 4. Now, when you graph that on your calculator, you actually have to graph root x plus 4, and then negative x plus 4. That's how, there's no plus minus sign on your calculator, sorry. Okay, now, if you flip the page, I actually graphed them for you. That's what I meant by I cheated. Okay, so look, so there's the line 3x plus 6, okay, and then there's the line 1/3 x minus 2. Okay, and the dotted line represents the line y equals x. Okay, so that's the reflection line. Okay, and you can very clearly see that those are reflections. Like, look at this guy right here. He's that far away from the mirror. Well, this guy is the same distance away from the mirror. Like, it's nice. You can really see it. Okay, and then for b, you can see that we have x squared minus 4, and then we actually had to graph the two functions, okay? Positive x plus 4 and then negative x plus 4. That's what gets the two halves of the parabola, okay, the sideways parabola, okay? And then you can see how they intersect on the line y equals x, okay? And so those are the invariant points, okay? It's kind of nice. Awesome. Okay, so key ideas. You can find the inverse of a relation by interchanging the x and y coordinates of the graph. The graph of the inverse and the graph of its relation are reflections or reflected in the line y equals x. The domain and range of the relation becomes the range and domain, respectively, of the inverse. Okay, we can use the horizontal line test to determine if the inverse will be a function. You can create an inverse that is a function over a specified interval by restricting the domain. And remember, that is always restricting over the axis of symmetry, or the axis of symmetry of whatever graph you're using. Okay, and then when the inverse of a function f of x is itself a function, it can be noted by f negative 1 of x. And then we can always verify graphically if the two functions are inverses of each other, because they'll look like these graphs above. You can tell that they're going to be reflections. And I always like to graph that line y equals x just to kind of see. All right. So I want you guys to practice this stuff. Okay, it's on page 50. Those are some good ones to start with. Okay, remember, you can always do more. It's not a problem. But guys, that's the lessons for chapter 1. So you have some formative assessments and some summative assessments to do for this chapter. So get started on those and give us a shout if you need anything. Okay, thanks. Bye.